After studying this module, you shall be able to learn about analyzing data with complex relationships, know about the complex research designs, assumptions and requisites underlying multivariate analysis, and briefly understand some of the multivariate methods. Introduction. In research, one often comes across questions that are best explained by designs beyond the simple research designs. As one can explore more than one independent variable by a suitable research design, similarly, multiple dependent variables too can be included through multivariate design. Strategy in a research. In complex designs, there are one or more outcomes or responses variables and several exploratory variables, together with many variables adding a characteristic particularity to the situation. These designs enable the researcher to study the effect of the independent variable on all the dependent variables and also on the composite dependent variable, which is formed as a result of weighted combination of all or some of the chosen dependent variables. For instance, professional achievement is directly related to professional skills learnt, but at the same time it is also determined by anxiety levels, communication skills, leadership traits, experience, professional wisdom, etc. So, in a study relating professional skills, professional achievement is a direct outcome, but other variables like anxiety levels, communication skills, experience, wisdom and leadership traits are also some of the impact variables. So, in a study relating professional skills, professional achievement is a direct outcome, but other variables like anxiety levels, communication skills, experience, wisdom and leadership traits are also some of the impact variables. Similarly, variables like family background, vicinity to the workplace, social support, etc. add peculiarity to each case. Multivariate analysis is a collection of methods used when many measurements are made on each individual or object in one or more samples. These measurements are called variables and the individuals or objects are called units, whether they be research, sampling or experimental units. The variables are measured simultaneously on each sampling unit and typically these variables are correlated. The goal of multivariate techniques is to simplify or express what is going on in terms of a reduced set of dimensions and explore, that is, generate hypotheses rather than test them. One would agree that a more complex statistical analysis would also be needed for a pragmatic analysis of such a data. The multivariate analytical techniques are a family of statistical techniques that analyze data obtained with designs where multiple dependent variables are used. These techniques draw on correlations among the dependent measures and are more useful than the several univariate analysis used on the data. Students' t-test, chi-square test are commonly used in psychological research analysis, and they analyze the effects of a single variable at a time and are part of a univariate and bivariate method of data analysis. Although the relationship between the outcome and explanatory variables are taken up by the data, the confounding variables often add as a contaminants to the results. But in real life, many factors may act simultaneously while others may just be confounders. The method of multivariate analysis take into account several variables acting together. The multivariate methods are connected with both descriptive and inferential statistics. In the descriptive domain, optimal linear combination of variables can be obtained since they have mathematical tractability and often perform well in practice. The multivariate methods are also useful as a follow-up to inferential procedures, where there is a statistically significant test result that compares several groups. One can find the linear combination of variables that lead to rejection of the hypothesis. Thereafter, the contribution of each variable to this linear combination is of interest. The multivariate analytical techniques cater to the both correlational and experimental research studies. The correlational multivariate design. This includes analyzing relationships between dependent variables in a correlational study. It includes a number of designs to study the complex correlational relationships. Some of the methods are multiple regression, discriminant analysis, canonical correlations, factor analysis, etc. The advantage of using these methods is that the complex relationships can be explored with minimal statistical errors. Also, they allow the researcher to understand the importance of an independent variable for interpreting the variability in the dependent variable, given the effects of the other dependent variable. The experimental multivariate design. In the multivariate experimental design, a number of dependent variables are combined on the basis of their correlational values and then analyzed with a single statistical test. Some of the popular methods are multivariate analysis of variance and multivariate analysis of covariance, that is MANOVA and MANCOVA. The advantages of using the experimental multivariate methods is that number of dependent variables are treated as correlated sets to reveal those relationships that might be ignored with univariate approach. Also, when all the dependent variables are dealt with using a single analytical technique, the chances of type 1 errors are reduced. Some of the restrictive assumptions of univariate methods can be overcome with these designs. Another application of multivariate analytical techniques can be found in drawing causal inferences or tentative results on the basis of correlational information among the variables. An example of such multivariate technique is path analysis. The present module discusses some of the popularly used multivariate analytical techniques, although the in-depth discussion of some of these methods is presented in subsequent modules. One must keep in mind that the complex and time-consuming calculations of these methods are best left to the computers. The module, however, does focus on the application and assumptions of the multivariate analytical methods. The important technical requisites to the application of multivariate method is also taken up in the coming sections, but for a detailed employment of these methods, one may refer to Rekov and Markulites 2008 editions and Tabachnik and Fidel 2007 and Stevens 2002 editions of their books on multivariate analysis. And one may see that a single sample with several variables measured on each sampling unit, you may do hypothesis testing, principal component analysis and factor analysis. When a single sample with two sets of variables measured on each unit, then one may go for a canonical correlation, multiple correlational analysis. Two samples with several variables measured on each, Hoteling's t-square, discriminant analysis, classification analysis may be taken up. When there are three or more samples with several variables measured on each, one may go in for MANOVA, discriminant analysis and classification analysis. Let us understand the assumptions and applications of multivariate analytical methods. Before one starts with the applications of the multivariate techniques on the research data, it is important to make sure that the data satisfies certain assumptions for these methods. the required assumptions of normality, linearity and homoscedasticity have to be checked. Assumptions underlying multivariate analysis. Linearity. The bivariate correlation methods thrive on the assumption that the two variables in continuous measures are linearly related. Any violations to these assumptions lead to error in statistics. The correlation coefficient may be an underestimation of the actual relationship among the two variables. As the multivariate methods are also based on linear correlation, among the variables, any deviation from the assumption of linearity of relationship among the chosen variables would lead to erroneous results. Of course, larger the deviations from linearity, more will be the underestimation of the relationship and the errors involved. The data can be checked for linearity by simply observing the scatter plot of the data. In case of non-linearity of the data, corrective measures like transforming the variables may be adopted to restore linearity. Normality. The bivariate parametric statistical methods assume normality of the population distribution. Similarly, the multivariate statistical methods also proceed on the assumption of normality for the population distribution underlying the sample distribution under study. The data might be skewed in some cases and require corrections. It is always advisable to carry out the required transformations in the data in order to restore normality. Homoscedasticity. Homoscedasticity refers to the assumption that the scatter of scores on a variable across a sample is approximately the same as all other variables. Or in other words, one may assume that all the variables being measured for a particular sample share roughly the same level of variance in the scores. Homoscedasticity and normality are two closely related concepts, as if two variables are normally distributed, show same degree of scatter throughout the distributions. The scatter plot of homoscedastic distributions would be elliptical, whereas the heteroscedastic distributions would show conical patterns of data points. The figure shows the two types of distributions. The heteroscedasticity occurs in a distribution if one or more variables included in the research analysis do not stick to normality. In order to check the heteroscedasticity in the data, normality needs to be restored and the data transformation needs to be carried out. Applications of multivariate analysis. The multivariate analysis methods are especially useful in observational studies, where total control is not possible, or intervention studies where complete control cannot be exerted, especially because these methods take into account the continuing relationships among several variables. Multivariate analysis becomes useful technique because it determines the structure of the data by discovering the underlying dimensions to describe data in simpler fashions. The multivariate methods provide multiple response outcomes as well as we shall see and explore in the succeeding modules. The techniques overcome the limitations of univariate analysis where there is just one dependent variable of interest. The multivariate methods help in study of a wider, more complex universe of subject data than what univariate methods offer in terms of analysis. Demand of data may be such that univariate analysis may not be possible. It looks at the phenomena in an overreaching way, providing multiple levels of analysis. Also, the multivariate methods offer a richer realistic design of research where multiple variables can be realistically explored. The multivariate methods can help in controlling the type 1 errors. Of course, there are limitations to the multivariate analysis, and some of them are that there is ambiguity in terms of less clear understanding of the data. The multivariate methods are complex and difficult to comprehend by novice. They have their own set of rules and assumptions, and that makes analysis difficult. It may require large sample size. Also, the methods are more difficult to interpret, as a detailed understanding of the method is imperative. The robustness of assumptions is not clearly established. The prerequisites of multivariate analysis. The dataset in multivariate complex research designs is vast and requires to be explored for certain preconditions before subjecting it to complex quantitative techniques. Along with the assumptions that the data also needs to be explored for requirements like outliers, multicollinearity, sample size and measurement errors. Some of these items were hinted at in the previous section while discussing the assumptions of multivariate analytical techniques. It is important to take care of these factors before the researcher proceeds with the application of the multivariate methods. As if they are not checked beforehand, they may lead to potentially serious damage to the valid data analysis. Outliers. The relationship between two variables can be looked at graphically using a scatter plot. A scatter plot is best explained by the line of best fit. Usually the least square criteria is used to statistically minimize the distance of scores from the line of best fit. If the research data has more points closer to the line of best fit, the prediction is more approximate and less of error is involved. However, if there are extreme scores, that is scores lying farther away from the line of best fit, these are called outliers, and these outliers disturb the slope of the regression line, thereby altering both the degree and the direction of the correlation coefficient. Univariate outliers are the scores deviating from a given point only. The multivariate outliers are the deviant scores on a combination of variables from a single source. Identifying the multivariate outliers. It is difficult to identify the multivariate outliers and therefore equally difficult to correct them too. The multivariate outliers can be identified statistically by calculating a statistic called Mahalanobis distance. The Mahalanobis distance is complex to calculate and is done through SPSS program. It is the distance between a particular data point from the mean of all the variables in the data. A significantly high Mahalanobis distance is indicative of a multivariate outlier and needs to be corrected. The multivariate outliers can be identified using the residual plot given by multiple regression also. The researcher should be very careful in identifying these outliers as they impact the results. Also, a repeated screening is imperative as some of the outliers have a tendency to hide behind others. Tabachnik and Fiddle, 2001. Correcting the multivariate outliers. There are several strategies that can be used to correct the outliers. Some of them are transformation of scores. We have understood while discussing the assumptions that any deviation from normality in the data needs to be restored. Any deviations from normalcy would have direct impact on the homoscedasticity and may cause outliers in the data. In order to correct deviations from normalcy, some of the methods available are positive skew when the data has moderate positive skew, then square root transformation on the scores bring desired corrections in the data. In case of more serious positive skew in the data, logarithmic transformations may help restore normalcy in the data. The negative skewness, when the data shows negative skew, the first step would be to use reflective strategy and transform the data to positively skewed one. The subsequent steps are then followed and the strategies used to correct the positive skews are taken up. The transformation strategies may prove helpful when the outliers are present in only one tail of the distribution. If the outliers are present in both the ends of the distribution, one may adopt other methods. First is of course the deletion of the outlier. Those subjects or variables that contribute to the outliers can be deleted completely from the set of data and they completely eradicate the impact. However, a major disadvantage of this method is that one loses on the collected data. This problem may further be magnified if the sample size chosen was small, and so deletion of outliers is possible only when the sample size is appreciably large. The other method can be the check for the source of errors. Sometimes the data may be contaminated by human or technical errors while entering the data on computers. The transcription and data entry or human errors while reading or entering the data in computers may cause outliers and thereby change the result and data analysis, resulting in wrongful results. Multicollinearity. Multicollinearity refers to the existence of a high degree of linear correlation amongst two or more explanatory variables in the regression model. Their presence makes it difficult to interpret their effects in data analysis. The relationship between the independent and the dependent variables can be explained easily univariate analytical methods. In the multivariate analytical methods, there are several dependent variables and the problem of analyzing the independent variable and dependent variable relationship may be magnified if the dependent variables themselves are highly correlated. This situation is called multicollinearity. The presence of multicollinearity in the data creates complexity in analysis and the best solution is to eliminate one of the two highly correlated variables. As high correlation among the variables indicate that the two are essentially measuring the same concept, eliminating one of them would not result in much loss of information. Error of measurement. Steps to arrive at valid results in research starts right from the time of its inception. Identification of the variables to be included to study the concepts and relationships and their measurement is of utmost importance. The difference between the true and observed values is the error of measurement. The observed values on a variable are function of both the true values and the errors of measurement. As the error value increases, the chances of underestimating the correlation coefficients using those variables increases too. Using these correlation coefficients to arrive at the multivariate statistic would lead to type 2 errors. So, any errors in measurement of the variables may lead to type 2 error in analysis. The error in measurement may also crop up as a result of biased responses, incomplete and inaccurate information from the subject. The tools used for data collection should be reliable and valid. Sample size. Among the major prerequisites for multivariate analysis is a large sample size. A large sample size ensures stable correlation coefficients and lesser chances of type 2 errors. The optimum sample size to be used for research study can be worked out by using the formula given by Tabachnik and Fidel in 2001 and should be greater than or equal to 50 plus 8m, where m is the number of predictor variables to be used in the research. One must add a word of caution here regarding the use of large sample size too. Having a very large sample size might result in significant correlation coefficients between variables and that may actually not share any useful and theoretical relationship. Let us have a very brief introduction to the multivariate methods. The multivariate analytical methods are mostly an extension of their univariate and bivariate counterparts. The multivariate techniques require large sample size and deal with large number of variables too. The methods are therefore difficult to understand and apply and require special computer statistical softwares like SPSS, AMOS, Lizrel and EQS for their mathematical application. In this section, we shall discuss some of the popularly used multivariate methods. On the basis of their applicability, the methods can be categorized under two broad classes. First, the multivariate methods used to study differences between independent variables, which are log linear modeling, multivariate analysis of variance MANOVA, multivariate analysis of covariance MANCOVA, multilevel modeling MLM, discriminant analysis, etc. The others are methods used to understand relationships among variables, which includes logit analysis, logistic analysis and regression, cluster analysis, canonical correlation, multivariate regression, path analysis, multidimensional scaling, principal component analysis, factor analysis, latent class analysis and structural equation modeling, etc. Let us discuss a brief introduction to some of the multivariate methods. Multivariate frequency analysis. The multivariate frequency analysis is a non-parametric multivariate statistical technique. The method is useful for categorical data, although it can be applied to interval or ratio scales also. One of the most popular forms of multivariate frequency analysis is log linear analysis. Hotelling's t-square is a multivariate counterpart of the student's test. The statistic is useful in research designs with more than 2 levels of independent variable and more than one dependent variable. MANOVA, the multivariate analysis of variance, is an extension of the ANOVA. It is useful with experimental designs that have many related dependent variables. MANCOVA, the multivariate analysis of covariance, is an extension of the ANCOVA. The statistic is useful when the variance contributed by one or more than one dependent variables needs to be controlled, so that the required variables can be studied with minimal influence. Multilevel modeling. The method of multilevel modeling is also termed as hierarchical linear modeling or multilevel analysis. This method is an extension of ANOVA or multiple regression, especially when the data lacks the independence. Discriminant analysis is an extension of the canonical correlation when the dependent variables are categorical in nature. The purpose may be said to be identifying the membership to a group on the basis of knowledge available on the predictor variables. Canonical correlation. The variables taken in the research can be grouped as two sets, set of dependent variables and set of predictor variables. The canonical correlation helps in computing canonical variate for each set. The canonical correlation is the measure of relationship between the canonical variates. Multiple regression. The multiple regression is used to analyze the extent to which each variable independently contributes to the variation in the dependent variable. Path analysis. This multivariate technique is an application of the multiple regression that is used to develop and test causal models using correlational data. Path estimates are derived using simple multiple regression, and then these coefficients are used to estimate the degree of relationship among the path coefficients to understand the causal relationships among the variables. Multidimensional scaling. The technique of multidimensional scaling is used to seek latent variables that can be identified on the basis of knowledge available in the data. The MDS explores similarities among the data collected on the variables and to seek if the set of information can be sorted on 2 or more dimensions. Factor analysis is a multivariate technique that makes use of the intercorrelations among the variables to extract the underlying common dimensions represented by them. The underlying common dimensions hence extracted are referred to as factors. The advantage of using factor analysis is that it reduces a wide set of variables in the research design to smaller and prominent ones. The factor analysis can be carried out in two ways: principal component and principal factor analysis. partial and part correlation. The partial correlation coefficients explore the relationship between any two variables in the research design by controlling the effects of the remaining variables. The part correlation studies the relationship between the two variables by controlling the effect of the third variable on either one of the two variables. Latent class analysis. The latent class analysis deals with data in categorical form. It can be seen as an alternative to some forms of cluster analysis. The latent class analysis can be carried out using special softwares like M+ and Latent Gold. Structural equation modeling. The structural equation modeling is a specialized technique that helps to conduct confirmatory analysis in testing a theoretical model. The SEM can be used to combine a number of other multivariate techniques in a single model only. The multivariate techniques are complex to understand and apply. Some of them have been discussed in detail in the subsequent modules. However, the readers must use them judiciously and preferably using special software packages. Summary. The multivariate analytical techniques are a family of statistical techniques that analyze the data obtained with designs where multiple dependent variables are used. These techniques cater to both correlational and experimental research studies. Correlational multivariate designs include analyzing relationships between dependent variable in a correlational study. It includes a number of designs to study the complex correlational relationships. In a multivariate experimental design, a number of dependent variables are combined on the basis of their correlational values and then analyzed with a single statistical test. The required assumptions of normality, linearity and homoscedasticity have to be checked in a distribution before applying multivariate techniques. The text also discusses some of the applications of multivariate analytical techniques. Along with the assumptions, the data also needs to be explored for requirements like outliers, multicollinearity, sample size and measurement errors for a valid application of the techniques. Multivariate analytical methods are mostly an extension of their univariate and bivariate counterparts. Some of the multivariate techniques like MANOVA, MENCOVA, multivariate frequency analysis, discriminant analysis, factor analysis, multiple regression, path analysis have been introduced to the readers in brief. The multivariate techniques require large sample size and deal with large number of variables too. The methods are therefore difficult to understand and apply and require special computer statistical softwares like SPSS, AMOS, Lizrel and EQS for their mathematical applications.